So let's finish off these videos on percentage composition, empirical formula, and molecular formula. So we've looked at how we can calculate percentage composition. We've looked at how we can go from percentage composition to empirical formula, remembering to set up our table with our elements at the top, work out the lowest whole number ratio. So now the last step in that is going from an empirical formula to a molecular formula. Okay, so remembering that the molecular formula of a compound can only be determined if the molar mass of the molecular formula is known. Okay, so we need to know how much 1 mole of the total compound weighs. Okay, we also need to know the empirical formula, so we need to know the ratio of each element in it for 1 unit. And then what we can do is work out that the molecular formula is a whole number ratio multiplied by the empirical formula. So I like to think of it this way. The empirical formula is sort of like the formula for our Lego bricks. Okay, so I may have a compound that is made up of 3 Lego bricks, okay, but this one, just this one unit here, is my empirical formula. The 3 of them put together is my molecular formula. The whole number ratio that ties these two together is 3, because if I have 3 lots of my empirical formula, I would be able to make this molecule. So what it's saying is that we need to know the total mass of the whole compound. We need to know what each unit of that compound is made, and then we can work out how many of them go into the whole. So let's have a look at how we actually go about doing that. Okay, so benzene has the empirical formula CH, and its molar mass is 78 grams per mole. So I have to have my empirical formula. I've got that, and I need to have my molar mass. I've got that. So that means that I can work out my molecular formula. Okay, so what we're going to do is work out the molar mass of each formula. Okay, so the molecular formula, okay, is 78 grams per mole. But if I work out the molar mass of each unit, so the molar mass of each individual brick, okay, it's 13 grams per mole. The molar mass of the entire tower put together, okay, however many these are, we don't know, okay, the entire mass of that is 78 grams per mole. Okay, so we know that one of these is a CH, and this is 13 grams per mole. So essentially, I know that the total thing is going to be 78. Each chunk that went into building it weighs 13. So if we think about that, the math should be straightforward. We take the molar mass of the whole thing, divide by the molar mass of one chunk, and that'll give us the ratio, the number of them that went into going together. So that means that we take the molar mass of our molecular formula, which is 78 grams per mole, and then we divide by the mass of our empirical formula, which is 13 grams per mole, and that will come out to 6. So the molecular formula is going to be 6 times my empirical formula. So when I put my bricks together, I'm going to have 6 bricks that go together. 1, 2, 3, 4, 5, 6. Okay, each one of those bricks is in the ratio of CH, which means that when I add all that together, it will be C6H6, or 6 times CH. And then when I write that out as a formula, I'm going to expand my brackets, and I get that. And that is, in fact, the empirical formula, the molecular formula of benzene, which hopefully you remembered, C6H6. Okay, so we're just finding out the ratio, how many of these individual units that is in our empirical formula, the lowest ratio, go into forming our overall molecule. So let's have another question. The taste of sour milk is due to lactic acid. The percentage composition of lactic acid by mass is 40%. Carbon is 40% carbon, 6.71% hydrogen, and 53.29% oxygen. And the molar mass is 90.09 grams per mole. Find the molecular formula. Okay, I can't find the molecular formula until I find the empirical formula, and I can find the empirical formula from my percentage composition. So we're going to, first things first, set up the table to find our empirical formula. So we're going to have carbon, okay, hydrogen, and oxygen. Go through and follow your steps. Assume 100 grams. These become masses, so 40, 0.00, 6.71, 53.29. Divide by the molar mass, okay, to get the number of mole. Have a go. Put me on pause, see if you can work it out, and then come back and I'll go through the solution with you. Okay, hopefully you paused me and you haven't just rolled on, but even if you have, let's have a look at how to work this out. So as we said before, we get the ratio of our elements, we write them down as they were in the question. Assume 100 grams, put our masses in. Now we need to work out mole, so we're going to divide by the molar mass of carbon, molar mass of hydrogen, molar mass of oxygen. That will give us a number of mole, which is equal to 3.33, 6.64, and 3.33. And hopefully you're going, hang on a second, Miss Ellis said if it looks exactly like a third, I'm probably going to have to do something with it. But not at this point, okay? This is our number of mole. Before we do anything about multiplying stuff, we actually need to divide by our smallest one, okay? So we're going to divide by 3.33. No multiplying here. Not yet. Okay, so we get 3.33 divided by 3.33, which is going to be 1, and get rid of that pesky 3.33. 6.64 is going to be 2 and 1, and we can see here we've gotten rid of those pesky hanging overs, so we're not multiplying by anything, we're just keeping it at CH2O. Okay, so that's our empirical formula. Now if we think back to the question, we had to find the molecular formula. It gave us the molar mass, so let's move on. Okay, so we've got to determine the molecular formula. We need the molar mass of each formula. So molar mass of CH2O, which is my empirical formula, add that all up, you'll get 30.03 grams per mole. Molar mass of the molecule, 90.09 grams per mole. This was given in the question. If you can't remember where it was, go back and have a read. So now I want to figure out my ratio, okay, which is just taking my molar mass and dividing by my empirical formula. And hopefully you can do that in your head and realize it's 3, okay? And that's what we've got all typed out here, okay? Which means that my empirical formula, I've got 3 lots of it in my molecule. So I've got 3 times CH2O, which is going to be C3H6O3, and that is going to be the molecular formula of lactic acid, which in fact it is. Okay, so hopefully you realize that if you follow the steps, you can't go wrong. Okay, one last thing. We've talked about hydrated compounds in the past, and we've talked about how that traps water away in the lattice, so CuSO4 pentahydrate here. So if we actually heat this, and we've talked about the theory of this before, if we heat copper sulfate, which is blue, it will actually turn white. And if we measure the mass before and after we do that, we can work out the percentage of, I've lost all my, whoops, there we go, zoomed in. Okay, we can actually work out the percentage of water and work out the ratio of water to copper sulfate. Okay, so what we're going to do is we're actually going to set this up as a ratio between CuSO4 units and H2O units. Okay, that's where we're heading with this. So the molar mass of copper sulfate pentahydrate is 249.5 grams per mole. Okay, the molar mass of water, hopefully we've figured out how to calculate this by now, is 2 times 1 plus 16, which is 18. But I've got 5 of them, so I'm going to multiply it by 5, and that gives me 90. So I can work out the percentage of water in copper sulfate pentahydrate by taking the mass of H2O and 1 mole of copper sulfate pentahydrate, which is going to be 90 grams per mole, and divide by 1 mole of the compound, back to our percentage composition. And that will give me, this is a little bit over it, but it'll give me 36.1%. So 36.1% of copper sulfate pentahydrate is actually water. Okay. We can work out the empirical formulae, okay, by doing the same process we did before. So we've got 5 grams, this is sodium carbonate, okay, form a hydrated ionic compound. 5 grams of the hydrated crystals, so this is Na2CO3 dot some amount of H2O, we don't know what, were dried, and 1.85 grams of Na2CO3 remained. Calculate the empirical formula. So what we want to do here is work out the Na2CO3 is to H2O. Okay, so we know that we have 1.85 grams of Na2CO3, and then the water is going to be 5, which is what we started with, minus what we got left with, and that will be my mass of water. We follow exactly the same process as what we did for percentage composition to empirical formula. We take our mass of water and divide by the molar mass of Na2CO3, divide by the molar mass, and that will give me the mole of each, okay, when we divide by the molar mass. And as you can see, I have 0.0175, 0.0175. So when we divide by the smallest, oops, so this should be, yep, that's a factor of 10 different. Whoops. Okay, so we get 1 is to 10. Okay, so that's telling me that I have 1 NO2CO3 dot 10 H2O. Okay, because I have 1 Na2CO3 for every 10 H2O. So I can work out the ratio of water to hydrated compounds. That can sometimes be a little bit confusing. Go over it, read over the copper sulfate one and this one again, and if you've got any questions, make sure you ask me in class. So that's it for all of our percentage composition, empirical formula and molecular formula calculations. We're going to get lots of practice of these in class, and we'll also do a practical experiment. So I'll see you in class.